Depth-first search, commonly known as DFS, is a fundamental graph traversal algorithm used in computer science and mathematics. The core principle of DFS is simple yet powerful. Unlike other traversal methods, DFS commits to exploring one path completely before considering alternatives. Think of it like exploring a maze by always taking the first available path and only turning back when you reach a dead end. Let's visualize how DFS works with a simple graph. We'll start at node A and watch as DFS explores as deeply as possible before backtracking. Notice how it commits to one path completely before exploring alternatives. Starting at node A, DFS first explores the path to B, then continues deeper to D. Only after fully exploring this branch does it backtrack and explore the path from A to C and finally to E. DFS has many important applications in computer science. It's essential for topological sorting, which orders tasks with dependencies. It can detect cycles in graphs, helping identify circular dependencies. DFS also finds connected components, grouping related elements together. To better understand DFS, let's compare it with breadth-first search, or BFS. While DFS explores depth first, going as far as possible along each branch, BFS explores breadth first, visiting all neighbors at the current level before moving deeper. Both are valuable, but serve different purposes depending on what you're trying to achieve. Depth-first search is naturally implemented using recursion. The algorithm explores as deeply as possible along each branch before backtracking, making it perfect for recursive implementation. Here is the basic pseudocode for depth-first search. The algorithm takes a starting vertex and a visited set as parameters. It marks the current vertex as visited, then recursively calls itself on each unvisited neighbor. The visited set is crucial for preventing infinite loops. Without tracking visited vertices, the algorithm could cycle endlessly between connected nodes. The visited set ensures each vertex is processed exactly once. Let's trace through a DFS example, starting from vertex A. We begin by marking A as visited and adding it to our visited set. From A, we explore its first unvisited neighbor B. We mark B as visited and continue the search from B. From B, we find unvisited neighbor D. We mark D as visited and explore from D. From D, we explore unvisited neighbor E. After marking E as visited, we find no more unvisited neighbors from E, so we backtrack. After backtracking to A, we explore the remaining unvisited neighbor C. Once C is visited, the depth-first search is complete. All vertices have been explored exactly once. In depth-first search, we track two important timestamps for each vertex: discovery time and finishing time. These timestamps help us understand the structure and behavior of our graph traversal. Let's demonstrate these concepts with a simple graph. We'll perform DFS traversal and track the discovery and finishing times for each vertex as we explore the graph. Now we'll perform DFS starting from vertex A. Watch how we assign discovery times when we first visit each vertex and finishing times when we complete exploring all of its neighbors. Now we continue from A to explore vertex C and its subtree. Notice how the timestamps create intervals that show the parent-child relationships in our DFS tree. These discovery and finishing times reveal important structural information about our graph. The time intervals show parent-child relationships, and we can use them to classify edges and detect cycles in the graph. During depth-first search traversal, we encounter different types of edges that help us understand the structure of the graph. DFS classifies edges into four distinct categories based on the relationship between vertices. Tree edges are the edges that are part of the DFS spanning tree. These are the edges we traverse when we first visit a vertex from another vertex. Tree edges connect a vertex to its children in the DFS tree structure. Back edges connect a vertex to one of its ancestors in the DFS tree. These edges point backwards in the traversal order and are crucial for cycle detection. When we encounter a back edge, it indicates the presence of a cycle in the graph. Forward edges connect a vertex to one of its descendants in the DFS tree, but are not part of the tree itself. These edges skip intermediate vertices and point forward in the traversal order. Forward edges are less common, but important for understanding graph structure. Cross edges connect vertices that are neither ancestors nor descendants of each other in the DFS tree. These edges connect different branches or subtrees of the DFS traversal. Cross edges help us understand the relationships between separate parts of the graph. One of the most important applications of edge classification is cycle detection. When DFS encounters a back edge, it indicates the presence of a cycle in the graph. This is because back edges create a path from a vertex back to one of its ancestors, forming a closed loop. DFS can generate a topological ordering of a directed acyclic graph. In topological ordering, vertices are arranged so that for every directed edge from vertex U to vertex V, U appears before V in the ordering. This is achieved by recording the finishing times during DFS traversal. DFS edge classification has many other important applications in graph algorithms. It can be used to find articulation points, which are vertices whose removal increases the number of connected components. It also helps identify bridges, which are edges whose removal disconnects the graph. These applications make DFFS a fundamental tool in graph analysis.